Thank you very much, Rowan. It is my pleasure to be here today talking to you all about upright patient positioning within radiation therapy and how I believe, or Leo Cancer Care believes, that that will define the future of radiation therapy going forward. So first off, one of the big questions to really ask ourselves, and it sounds very profound, but what really is the future? When we talk about something being the future, what do we really mean? It's very easy to imagine a scenario where you picture a very futuristic and almost sci-fi city with cars flying everywhere, but that's not really what we're talking about when we're talking about the future of healthcare. And if you look up the actual definition of what the future really is, we talk about a period of time following the moment of speaking or writing, time regarded as still to come. So essentially, anything that is ahead of us purely from a time perspective. But that could be a second ahead of us or a minute ahead of us. Again, not really what we mean when we say the future of healthcare. To me, when I say something is the future of healthcare or the future of radiotherapy, I'm really talking about something where a point in time where we have a significant improvement compared to what we're doing today. That's really, to me, what the future means. What we're doing today has got us so far, but what happens at some point further down the line where we've got a significant improvement? And really those improvements, to me, it could be an improvement in the clinical effectiveness of what we're doing, so being able to treat patients better, being able to offer an improvement in the availability of care, so more people get access to the technology, or it could be improving the patient experience, making it more comfortable or less daunting for patients to receive the care that we're talking about. And I'm going to focus my argument on the future of radiation therapy on these three areas. So second question, what is radiation therapy, I guess, to start things off here? Well, when we think about cancer care, we typically think about three main pieces to the puzzle. We think about surgery, where you open the patient up and you cut the tumor out. We think about chemotherapy, where we inject drugs into the body, and that effectively poisons the tumor. And the third treatment technique that we talk about commonly is radiation therapy. It's radiation therapy that we're going to be talking about today, but it's the one that people are less aware of and less comfortable with. So broken down very simply, radiation therapy is essentially the act of placing somebody lay down on a table and then taking a very large machine that weighs anything from 6 tons to 600 tons that produces a high energy radiation beam and rotating that around a patient, delivering radiation beams from different angles. And the intersection of those radiation beams, we position the tumor and we effectively burn the tumor out of the patient. That is radiotherapy in a nutshell. And it's a vital weapon in our arsenal to treat cancer. 50% of all patients that are diagnosed with cancer should receive radiation therapy as part of their treatment. The reality is, and we'll come to this a little bit later on, but the number that actually do is more like between 25 to 40%. And when we think and talk about radiation therapy, there are a couple of real principles that lie at the center of this treatment technique that we really don't question very often. We treat patients with lots of different types of radiation, everything from electrons to photons, all the way through to things like carbon and helium. And we generate that radiation with many different types of accelerator, different types of machine, from linear accelerators all the way through to the really big synchrotrons. And we treat many different indications, many different types of cancer with many different machines which look very different to each other. But really, through all of these differences, there are two core ideas that we don't question very often. The first of those is that patients are treated lying down in the majority of the systems we look at today. And number two is that the radiation or the machine rotates around the patient, not the other way around. So why is that? Why are those two ideas central to this technology and these treatments? Well, the idea of rotation is really essential. If we look here on the left, we can see a scenario where we treat with only two beams with photons here. And what happens is that you effectively treat all the way through the patient and you get a very uniform distribution of dose throughout the patient in doing this. Now, what happens is if you rotate and deliver radiation from different angles, is that you actually spread the entry dose and the exit dose, and the only bit that lies at the center of all the beams is the tumor. So you build up a very concentrated dose at the tumor and spare the healthy tissue. So this is essential for delivering high quality radiation therapy. And then looking at this second idea, this idea of patients being laid down on a table flat on their back. Where does that idea really come from? And if you look at radiation therapy treatment, it's guided and goes hand in hand really with imaging. You need to be able to know where the patient is, know where the tumor is to be able to deliver the therapy. So you've got to have imaging that sits side by side as treatment. And for many, many years, things like CT scanners and MRI and PET scanners, they've all been developed in the supine orientation for the patient. So these two technologies have driven each other forward for many, many years. But if you ask me, one of the biggest reasons that we have these two core ideas central in all of the treatment techniques is this attitude as an industry that we've always done it this way. We say, well, if it's not broke, why fix it? But the reality is we could have taken that exact same attitude with many types of technology, not just in the healthcare space. But thankfully, all of this technology that we're looking at on screen today has been improved upon. We've continued to drive improvement. And thankfully today, we're not using floppy disks anymore. We're not using old Nokia phones, but all of that technology has been integrated into one device that really rules our lives today, the smartphone. So at Leo Cancer Care, and what I'm going to be talking about today, we're really challenging, questioning those two core principles and really exploring how that can drive the future, as we're talking about here, in radiation therapy. So by treating patients in the upright orientation, and we'll go on to and explore in the rest of this talk, we believe that that will improve the clinical effectiveness of the treatments that we're delivering and also drive a better patient experience for those people that we're treating. And by keeping the radiation fixed and not having to rotate these large machines, that will undoubtedly reduce the cost, the size and complexity of devices, and therefore improve the availability of care and access to these treatments. And by bringing those three core ideas together and driving improvement in each of them, that is what gives me the foundation to make this statement that the Leo Cancer Care technology will drive the future of radiation therapy. So let's start exploring those ideas. Let's first look at the clinical effectiveness. This is really the most important out of those three. And if we look at the World Health Organization and the distribution and the breakdown of the patient population by indication, we can see that 22% of cancer incidences relate to lung cancer. An equal number, 22%, relate to breast cancer, 13% to prostate cancer, and 9% to liver cancer. Now, I've pulled these four specific indications out because I'm going to walk through now very solid clinical evidence that suggests that not only could we treat these patients in the upright orientation, but indeed the evidence would suggest that maybe we should be treating these patients in the upright orientation. There are other indications, things like head and neck, for example, where we could treat them in the upright orientation. And indeed, there may be some benefits there, such as improved tongue reproducibility. But there's not a great deal of evidence today to suggest that we really should. There's a desperate need to be doing so. So we're just going to look at these 4 indications specifically. So first off, let's look at lung. And a group over at MD Anderson Cancer Center in Houston, one of the biggest in the world, that group led by Lawrence Court, who's on our scientific advisory board, looked at the magnitude of breathing motion, the magnitude of lung motion that you get when you've got patients lay down, and compared that to patients in the upright orientation and published these data. And you can see here in red the magnitude of breathing motion for patients lying down, and the same patients then, again, the magnitude of breathing motion, but in the upright orientation. And the conclusion of this paper and these data was to say that actually the magnitude of breathing motion can be reduced by up to 4 to 5 millimeters just by having the patient in the upright orientation. So why is that? Well, the paper looked at imaging patient volunteers, both supine and upright, and showed, as you can see here in this image, the same patient, the same phase of the breathing cycle. The only difference is that the image on the right is the volunteer in the upright orientation, and the image on the left is the same volunteer in the supine orientation. So you can see a much larger lung volume when that volunteer was upright. And then for the same tidal volume of air, when you're breathing in and out, having a larger lung volume results in a reduction in breathing motion. It's kind of like if you think about taking a water balloon, a very, very small balloon, and you take a very, very large balloon and you push in the same measured quantity of air, you will observe a much larger motion in the small balloon than you will the large one. And what's the amount of volume that we're talking about here? Well, in this study from MD Anderson, the average was around about 25%. But in some cases, they showed that the lung volume could be more than 50% larger just by having that patient in the upright orientation. So what's the deal? What's the importance of this? Why is this relevant? Well, it's pretty easy and pretty well known that if you're trying to target a tumor and trying to target it very accurately, it's much easier to do so if it's not moving quite so much. It's the same if you were trying to shoot an arrow or fire a gun. It's always much easier to hit a target that's not moving so much. So let's look at the second indication here. Let's look at breast cancer. Now, imagine a breast cancer patient that's treated lay flat on their back. The breast tissue would fall down on top of the patient, meaning that the tumor that's in the breast tissue moves closer to the heart and closer to the lungs. And that's exactly what you see here on the right. And what happens here is when you're trying to, again, target accurately the tumor, having the tumor move closer to those organs at risk means that you undoubtedly then deliver unnecessary radiation dose, unnecessary toxicity to the heart and to the lung. And this is what causes secondary side effects in cancer patients. So this is a very, very well-known fact. And actually, you're 38% more likely to develop secondary lung conditions, secondary heart conditions, if you receive radiation therapy as part of your treatment for left-sided breast than if you don't. So people for many, many years have explored lying the patient flat on their front and bringing the breast tissue away from the chest wall, increasing the distance between the tumor and those healthy organs, and therefore getting a better dose distribution. But it's very, very difficult to set a patient up, lay on their front. It's very uncomfortable for the patient. It's difficult to get reproducibility, and it's difficult to get visibility as well. So the same group actually over at MD Anderson looked really for a best of both worlds to treat breast cancer patients. And in fact, treated them seated and leaning ever so slightly forward. And in doing that, you still bring the breast away from the chest wall. You still increase the distance between the tumor and the organs at risk, but you do so in a much more reproducible fashion that allows you also to get better visibility of the patient during setup. So what's really important here in this change? Well, think about it like this. This scenario on the left, and this is a well-known scenario where you put the apple on the head and you ask somebody to shoot it off. Why is this such a daunting thing to think about? Well, the reason is because the target, the apple, is close to something that you really don't want to hit. If you imagine a scenario where you increase the distance, exactly as we're talking about with the tumor and the lungs and the heart, you increase the distance between the thing you want to hit and the thing you don't. It gives you much more confidence to deliver, in this case, the arrow, but also the same with radiation. Now let's move on to looking at the liver. And again, before I get onto the deep clinical stuff here, just think about a day in the life of a cancer patient when they're receiving their radiation therapy. From the moment that they wake up in the morning to the moment that they lie down again for their treatment, everything else that they do in their day, whether it's standing to get dressed or walking or sitting to eat breakfast or driving, from the waist up, everything that that patient does, they do in the upright orientation. And what happens then is that their organs stabilize in this period. The direction of gravity relative to their organs stays exactly the same, which makes this point here where the patient lies down again very interesting indeed. And a group led by Tony Lomax at the Paul Scherrer Institute over in Switzerland analyzed what happens to the internal organs as the direction of gravity relative to them changes when we ask the patient to lie down. And they acquired MRI sequences of volunteers and monitored what happened to those internal organs. And they showed that over a course of around about 35 minutes, you see a very slow and reproducible drift in the organ position. So the point that you start treating, 35 minutes later, it's in a different position because the organs have moved. And they noticed this for a number of different organs, but most noticeably for the liver due to the rest of the internal anatomy that surrounds it. And the amount of motion that we're talking about here was around about 20 millimeters. So this doesn't sound very significant for the majority of things you measure in day-to-day life, but in radiation therapy, 20 millimeters is very, very significant indeed. So let's talk about prostate now. One big problem that we have when we're treating prostate cancer patients comes with this link between the shape and the position of the prostate as a function of how full the bladder is. So if you were to look at somebody with an empty bladder, then their prostate would be one shape and in one position. And if you look at the same person with a full bladder, it would be in a different shape and a different position. Now, this means when we're treating patients today supine, that we have to always come and always treat them with a full bladder, which is very uncomfortable for the patient, but it's also very difficult for the clinician to set a patient up with a full bladder, because what really does that mean? What really defines full? Very difficult to pin down. But if you see here, we've acquired MRI images of volunteers, both supine and upright. And if you look here, you can see the contour in light blue for the prostate with dotted lines for an empty bladder and solid line here for a full bladder. And you can see that this has gone from completely empty up to full, but the shape and position of the prostate really hasn't changed. So why is that? Well, the reason for this is really due to the abdominal content and the force that applies on the prostate in the supine and upright orientations. Now, when you've got somebody upright, the gut, especially for people with larger guts, really comes down and applies a strong force on the prostate. And that compression of the prostate really holds it in the same position, regardless of the level of filling of the bladder. And that's not the same in the supine orientation. So there's a lot of work still to do here. There's a lot less coverage in the literature, but the suggestion would be that we could move to a scenario where we can treat patients with a half full bladder rather than insisting on a completely full bladder. So that really deals with the clinical advancements that we're talking about here. Now let's look and move on to patient experience, what this change in the way of delivering radiation therapy really does for the patient. And there's a little bit of a common misconception when we talk about this change from treating patients like lay down to treating them in the upright orientation. People think, surely it's more comfortable to be lay down than it is to be seated or stood. And if this picture on the left was the reality, and what we were looking at was treating patients on a comfortable bed, then I would absolutely agree with that statement. But the reality is very, very different. We ask patients to lie on a very hard tabletop, often with an exposed spine, and that is a very, very uncomfortable position, even for healthy people to lie down in. But imagine being a lung cancer patient or an esophageal cancer patient. It's very, very uncomfortable to be treated supine today. And I want to share with you all a quote, a statement that I had from a patient that I spoke to at a support group over in Sydney, who said to me that when he found out he had cancer, he thought he was dying. And like many patients, said that was the most terrifying experience of his life. But when he was asked to lie alone in a very clinical room on a hard table, he felt like he was already dead on a slab in a morgue. And while that is a statement, a quote from one patient, and it's a very, very extreme and very emotional statement, it does get you thinking about how we as humans really feel and cope with difficult situations when we're laid down on our backs. And when I started putting this presentation together, I went on Google and just typed in sick patient. And the first 5 pictures that come up on Google are what you can see there on the left, all in the supine orientation, all with the patient lay down in a hospital bed. Now, I also typed into Google the word empowered. And you see there on the right, the images that come up there, the first human images that come up, very, very different. But what you notice with every single one of them is that the human in the picture is upright. They are on their feet, because it is natural as humans that we feel in control of the situation that we're in when we are on our feet. We even say things like, don't face this lying down. It's much more empowering for patients to be upright. They feel like they're in control of their situation. And it goes beyond the work that's gone into looking at this improvement in patient experience, goes beyond just anecdotal or subjective feedback. Lawrence Court's group, again over at MD Anderson, went and asked patients what they thought about being positioned in the upright orientation and whether they deemed it acceptable to be treated upright. And the results were resounding. There is no issue from those patients with the idea of being positioned upright. What does the idea of keeping the radiation source fixed and slowly rotating the patient, what's the effect on the availability of care? Well, first off, let's just have a very quick look at the state and the distribution of radiation therapy across the globe today. And again, this from the IAEA shows that there are, without a doubt, a number of countries across the globe which really don't have an issue with access to radiation therapy. Unsurprisingly, this is places like the US, many parts of Europe, Australia, Japan, don't have access and have enough access to radiation therapy today. But there are parts of the world which that is simply not the case. And many countries still, that don't have a single radiation therapy system installed. Many places in South America, Africa, and Asia that simply don't have the access that they need to radiation therapy. And these very shocking figures, I think, show that in high income countries, these really developed countries, one radiotherapy device might serve 120,000 patients. In low income countries, developing countries, that number might be 5 million. The same device now has to serve 5 million people. So we still have globally a very, very big issue with access to radiation therapy. So why is that? What still causes this problem? Well, put simply, the size, the cost, and complexity of existing technology today makes radiation therapy devices completely out of the question, completely unobtainable for many, many hospitals all over the world. And to put this into some perspective, and to give you a little bit of an analogy and an easy way of thinking about this, think about a light bulb. And this might sound odd, but a light bulb is something that we all can picture. We've all changed a light bulb in the past, and it's a very, very easy thing to think about. We all know that you've got your light bulb and you've got your fixture that it must go into. And we know that something has to rotate with respect to each other here so that you can securely get the light bulb in the fixture and make the connection so that the light bulb turns on. And we all know how to fit a light bulb. It's a pretty easy thing to do. You take your light bulb and you rotate it within its fixture until it's secure, and then you can go and turn the light bulb on and it works. But actually, there is a second option. There is an alternative to fitting a light bulb. You could go and rent a couple of cranes to come in and pick up your house and slowly rotate your house around you while you stand there with your fixed light bulb. The same thing would happen. You would rotate one with respect to the other. But rather than rotating your light bulb that weighs a few grams, you've now rotated your house, which weighs a few tons. And this to us seems crazy. You know, I'm saying this a little bit tongue in cheek, but no one would ever do this because we know and we understand very clearly that rotating the lighter object is much less expensive. It's much more straightforward. And the scenario, the system to do it is much, much smaller. So what about if we took the same approach, the light bulb approach, with radiation therapy? And to give you an idea today, this is a particle therapy comparison for protons. To give you an idea today of the size difference that we're talking about, a typical rotating gantry room for particle therapy will be not far off 1,500 meter cubed in volume. The alternative of keeping the radiation source fixed and rotating the 100 kilo patient rather than the 100-ton rotating structure is that you bring that volume down to around about 90 meters cubed. That is a reduction by a factor of around about 16. Very, very significant. So what does that do for you from a cost perspective? Well, again, you can see these two systems side by side, the same radiation that fuels them both, but you've only changed the fact that you're rotating the patient, not the structure. And now, rather than building a brand new standalone center that is a 3-story building for this rotating structure, you could look at a scenario of installing these same devices in existing hospitals. So it takes your building costs, and these building costs are indicative. They vary broadly and tremendously. But you could take your cost of a brand new center down to a renovation cost. So a very, very significant reduction purely on the building. The hardware itself, by removing all of this hardware, you can bring the cost down from around about 22 million, again, significantly down to around about 15 million. And that, coupled with the clinical benefits of treating patients in the upright orientation, very, very significant. And aside from just the capital costs and the equipment, the building costs, We also can see a significant benefit operationally as well. It's just a very crude cartoon that shows the process of sitting somebody down, where you walk them in and sit them down, and the additional steps required to bring in support clinicians to support the patient as they lie down. These additional steps add additional time into the treatment workflow. And there's been a group over in Japan that has studied this in detail, looking at how long it takes to set somebody up upright versus supine. And we've done some studies as well internally. And this setup time difference between upright and supine, if you add all of these up, brings you down to around about 6.5 minutes faster per treatment in the upright orientation. So very significant operationally as well. So where does that lead us then? We've talked about benefits, potential benefits from a clinical perspective, from an availability and an access to care perspective, and from a patient experience perspective. So how is Leo Cancer Care harnessing all of that benefit, and what technology are we bringing to the market? So the Leo Cancer Care approach to delivering radiation therapy is very, very simple. We start by looking at the patient and optimizing their patient posture. And we do this based on indication. And it's actually the case that your posture and the best position to treat somebody in is not the same for all indications. So if you're treating somebody for head and neck cancer, in an ideal world, what you really want is for the arms to drop naturally by their side under gravity, so that you can completely open up the neck region to deliver those head and neck treatments very easily. Now, this position is in fact different, as we talked about, for breast cancer patients, where in this scenario, you want to reproduce that position that the guys at MD Anderson did. So have a patient in a seated position and lean them slightly forward to bring the breast away from the chest wall. And then, as we talked about with prostate cancer, the optimum position there is really the important bit, is to have the patient in the upright orientation so that we can secure and put more pressure and constraint on the prostate. But we need to do that in a way that completely opens up the pelvic region. So a conventional seated position would not work here for prostate cancer. But if you have the patient in what we term the perched position, where their weight is distributed across their shins, across the backs of their heels, across the seat pan, and also supported by their arms as well, in this scenario, we have an optimum position for treating prostate cancer. So then, once we've optimized the patient posture, the second step is to bring the imaging technology into the isocenter around the patient. So we do this with our dual energy diagnostic quality CT, as well as other things like proton radiography and prompt PET, for example. Much easier with all the space that you have around the patient when they're in the upright orientation, much easier to bring this high quality imaging technology to the treatment isocenter. And then what you can do with that imaging and patient position fixed, then you start thinking about bringing the radiation source in. Not the other way around, not starting with the radiation, but first getting everything set with the patient. And that radiation source could be photons, it could be any particle, it could be protons, carbon, helium, it could be things like neutrons. Really, the advantages to this approach are exactly the same. So you've got your patient posture, you've got improved imaging at the isocenter, and you've got your radiation source. The final step then is to deliver the radiation. To deliver the radiation from different angles, we simply rotate the patient very, very slowly, the same kind of speed you would rotate comfortably in an office chair, but we do that in front of the fixed radiation beam. So a much more straightforward and logical way of delivering radiation therapy. So specifically, what technology and how does this come to life with the Leo Cancer Care products? Well, we're operating in the particle therapy space with third-party radiation providers. So we're not producing particle therapy beams. We are simply providing the patient positioning system and the isocentric imaging device to guide particle therapy treatment delivery without the need for the gantry structure. In the photon radiotherapy space, we are taking the same innovation, the same core benefits of our rotating upright patient positioning device, but this time integrating it into our own complete integrated treatment delivery device. So putting a horizontal linear accelerator together with an onboard integrated CBCT system and rotating the patient now in that imaging and treatment volume. And what's really interesting here is that whether you rotate your imaging and treatment system around the patient, or you rotate your patient within that imaging and treatment volume, the images that you produce and the dose distributions you produce are exactly the same. But you're doing it in a more compact, more sensible, and cost-effective solution. And what's more, thinking outside of just the device, the hardware itself, this idea of keeping a radiation source fixed and only pointing in one direction, and instead rotating a patient, allows you to integrate the radiation shielding into the system because you only have to primary shield in one direction. So you have the ability to completely encapsulate the radiotherapy device with this very, very compact shielding unit, which takes you away from thinking about specially designed bespoke radiation bunkers to a complete integrated proven radiation therapy device. And what's more, that exciting idea of a self-shielded radiotherapy system opens up the prospect of taking radiation therapy to places that it has never been before. Decentralized healthcare, the ultimate satellite center, taking high quality radiation therapy to the patient, not the other way around. And finally, supporting both of those innovations in the particle and photon therapy space is our standalone dual energy diagnostic quality CT system that can be used for CT simulation, but also many other applications in radiology. Things like imaging the spine, imaging hips, imaging the knees, anything where really the patient should be imaged, load bearing, weight bearing. And the CT imaging system that we've developed is a multi-axis device. So it's capable of imaging patients in the upright orientation, but also supine as well. So the innovation and the thinking outside of the box to explore the idea of upright positioning and fixed radiation beams is allowing us to innovate many, many different areas within the healthcare system. So coming back full circle then, we've looked at the idea of positioning patients upright, and we've looked at the idea of keeping radiation fixed, and we've shown the great potential to impact and affect clinical effectiveness, patient experience, and the availability of care. And for me, an impact across all three of those areas is really the reason why I'm saying that Leo Cancer Care and the idea of upright patient positioning will drive the future of radiation therapy going forward. Thank you very much for listening. It's been my pleasure to speak with you all today. Thank you very much.